Alright, this is the first documentation video for EvilVM. EvilVM is a programming language or development environment designed for writing malware. When I say malware, I'm talking about this from the information security industry perspective. I've been a penetration tester, I work with red teamers now, and a lot of times what you're doing when you're doing a security assessment, if you're hacking somebody, what you're really doing is writing malware. So I use the M word. I don't think that this is intended for dark use. This is intended for white hat use. But I feel like this has been a really great project so far. I had a chance to present it at NolaCon. You can find the presentation there if you want a lot of background. But for this video, I'm just going to walk through installation of the system and show a little bit of use of it. Just hopefully have a short little video that is a good enough intro so that maybe if you saw the talk at NolaCon or something, but it's not really clear how you can actually start playing with it yourself, hopefully this should get you up to speed. So to start with, we'll just grab the repo right out of GitHub. And in this case, I'm doing this on a basic Ubuntu system with Docker installed. So Docker is a handy way to do this. There are some prerequisites and other things that are annoying enough to get set up. So if you're on the Docker bandwagon, this will be sensible for you. For myself, I'm not really an expert with Docker. I've only used it a little bit here and there. So if as we go through this, if you feel like I've missed some opportunity to do it even better with Docker, let me know. But since we were talking about having a cross-compiler and there's some dependencies involved to get everything working smoothly, this turned out to be a pretty easy way to do it. So we'll just create a Docker image, name it EvilVM, and there's a Docker file right in the repo, so this will get us off to the races. This takes a little while. It ends up building a few things along the way. It compiles a custom version of, or not custom, but an up-to-date version of NASM. The ones that are in the NASM in the Ubuntu repositories is old enough that it's not good enough for disassembling chunks of code from memory on real 64-bit machines. So I'll let this run, and then I'll resume the video once it's done setting up. Okay, the last phase of the Docker install is to compile NASM, like I said. So once this is up, we should have a place where we can execute all of the main components. Obviously, you can do all this pretty easily on your own machine if you want to set everything up, but I think this is kind of a handy way to jump into it. So we have a EvilVM Docker image. It has to have that name for the scripts to work. But we can use this as an entry point for all of the functionality. In the repo, there's a command called EvilVM. This is just an entry to some shell scripts that handle all the Docker glue underneath. I like to link this into user local bin so I can run it from anywhere. If I had some place where I wanted to store my files and not always keep them in the EvilVM repo, then that kind of makes it handy. So this allows us to be just about anywhere, and we can run EvilVM. So EvilVM is really three things. It's a server, it's potentially some shims that allow you to connect to other network protocols into that server, and then there's a tool for building the agents. The agents themselves are the actual compilers. They run on the target system and connect back to the server. The server only speaks TCP, and so you can use shims for other protocols. Right now there's only one, it's HTTP. But by splitting this out, it means that each different I/O layer can have its own way of doing things, and it just has to back-end everything with a TCP connection into the server, and it keeps the server really simple. So to start with, let's build some agents just for demonstration purposes. When I run the build functionality, we get a help output. You can choose your transport layer. You can decide on what your options need to be. There's some other things too, just for trimming up the shellcode or doing other interesting stuff. We can export it into different formats. For now, we'll just make some executables. So we'll choose the network I/O layer. This is just the standard TCP connection. We need to connect somewhere. Actually, let's find out where. That's where. If I could type while recording. Default port is 1919. Yeah, you can change it if you want to. and we'll just export as an executable. You can also do this directly to shellcode and use whatever stager or loader you wanted to, or embed it in some other program. For demonstration purposes, it's easy just to do it this way. They tend to be pretty small. So let's do one with the HTTP endpoint. So HTTP defaults to port 1920. That way they can listen on the same system. And we also have to specify the URL. By default, I do /feed. All right, so we have these two things. Now, this demo scenario, I'm just assuming I have command execution. I can move these binaries up to the target system and run them. I could run them off as share or something if I wanted to be creative. But I'm not doing anything fancy for delivery. You can be fancy if you want to. So I have a system that I've chosen. It's just one of my test VMs. So we'll just upload those. Oh, let me think here. Oh, I already have one of those. Interesting. I use this VM for testing all kinds of stuff. So once we have that, we could run them, but they wouldn't be able to connect anything because there's no server running. So let's just run the server. So and once this is running, we're bound to 1919. You could either change where it listens if you wanted to change the port, or you could just use SOCAT or some other thing to sit in front of it as a relay. So let's log into that box. Oops. Okay. So this is just a regular Windows box I use for testing. And if we look, there's our these are our agents I just put up. So once these run, they'll connect back. Let's just start with the TCP agent. And then we have a working connection. So connections come in, they announce themselves with some information. This mostly just ensures that the initial contact is not always the same sequence of bytes. I felt that was handy just for making detection a little bit harder. And then each one is assigned a Crayola color, and that's based on this ident string here. So username and host name, and then this is the machine GUID. Ideally, it should be unique for each box, but might not be if you cloned a disk image, but hopefully then you got different users or something. It just helps you identify them and differentiate between them. And then if we want to connect that other agent in, and we want to do the HTTP interface, let's grab another shell here, and let's run, so shims, we've only got one shim available, HTTP. So there, once this is running, it's just waiting for HTTP connections. Once one comes in, it'll associate a connection, make a TCP connection over to the main server, and we'll get communication with it. So let me grab up another terminal over here, just so there's nothing up my sleeve. We'll run http2.exe. So we can see we get an initial announcement. That's just that first little bit, and then the server sends down the core API. This is actually a combination. It's the language's core API plus the default network payload, which has some other stuff that's kind of handy. And then you can see it regularly pings to see if there's more data. If we hop back here, and what we'll see here is that we now have channel number 2. And we can have any number of channels that we want. We can see them by interacting with the server. Right now, everything I type in will interact with the agent, but I can issue a control K. And on my keyboard, I do that with control V, control K, so that I make it a literal control K character. And then I can list my agents. And I can switch back and forth between them. So if I switch to client number 2, then we can see all of the queued up output from that agent since the last time we talked to it, which was never, since it just came in. And this one, of course, is the same user and the same machine GUID, so it still gets the same color. You can see, though, it's coming from localhost because it's bounced from that shim process. Now, working with this agent, because it's HTTP, is a little bit slower. So say I run the banner function, and that shows me the language banner. It's a little bit slow, and that's just because of that polling interval. I can actually change that. Let's grab, so you can see how the pings are coming in approximately every 5 seconds. In fact, it is exactly that, I think. So there's a delay variable that stores how often it checks, and then we can read the value of that variable and print it out. So these are standard forth primitives for reading the value of a variable or a location in memory and printing the value at the top of the stack out to the standard output. So we can see 5,000 milliseconds. That makes sense. We can change that. Let's make it a quarter second. And then we'll see that once the agent checks in, now we've got 4 times a second it's checking to see if there's data. So we'll be much more responsive now than it was before. Or we can do things like 60 seconds delay sets. This is the counterpart to the @ signs. This sets the value. And now it'll be a long time before it checks back in. So what can we do with an agent, you might wonder? So you've already seen a couple things. One is I can interact with system variables like the delay for the HTTP transport, but there's quite a bit in here. If I enumerate the contents of the dictionary, each of these is a function. So these functions include basic primitives like doing math. So somewhere around in here we should find here's addition and subtraction and division. But then other things like the compiler itself is defined here. And then some things that are much more user-friendly, intended for the end user to use. So part of the default network payload, we get some basic functionality. So we can do things like get our bearings, find out where we are, enumerate the contents of the file system, etc. This is a test box, so who knows what's in here. We can run commands too if we want to execute OS commands and find out who we are. But there are other things we can do. We can define new code, so we can interact with this like it's a REPL and just compile some code. Let's do hello world. So this is some basic forth here. The colon is how we start a new definition. We give it a name. Dot quote reads until the next quote as a literal string that will get printed at runtime, and then semicolon terminates a definition. So we're defining a function called hello, and it does the hello world functionality. And then we could do something maybe a little bit more complicated. So this is a stupidly contrived example, but here's a function that prints out that something is odd, and something that prints out if it's even. And then here's something that checks if a number is even or odd, and then calls the associated function. So easy way to check if it's odd is to AND it with the number 1, and then if that's not 0, then we say it's odd, and otherwise we say it's even. Right, so this is just some forth code's basic conditional. And then we can write a little test program that does a loop. So let's do from 0 to 9, so this is 0 below 10, do I parity loop. Right? And so now we have this stack of functions that we've implemented, so we can run them. Oh, and I forgot the thing. I forgot .post. There we go. I'm going to keep it as pretty as possible. So this way we can see, which numbers are even and which ones are odd. But this hopefully gives you an example of how we can stack up code just like any other programming language and make things more and more complex as we need to. So the other thing we can do is we can send code we've already written. We don't always have to do it interactively. We can have code written in files. And in fact, if I grab another terminal here, in the repo there's a directory called samples, and this has all of the code samples that I at least package with EvilVM. And some of these are more like proofs of concept, and then some of them are more useful things like clipboard monitors the clipboard. I mean, every time the user copies something, if it's text, it gets printed out in your console, so you can see if someone copies and pastes something interesting. So some of these are actually weaponized functionality already, and then some are more like libraries or interesting tests. We can send these to the agent by once again interacting with the console, so Control V, Control K, and then we can load code, and if I just provide a bare file name, it'll be one of these in the samples directory. I can also provide a path to it if I wanted to. So let's send, here's a good example, I think. This is one I gave in my talk at NolaCon. Sometimes you're working with a system and you don't want to be detected, and so you want to get information about the environment, but if you do it the normal way, it's more likely to show up on incident responders' radar. So for example, if my agent were to run the netstat command to get information about the network configuration or its current state, it would work, I would get the information, but at the same time, it might show up in an execution path that gets logged by an EDR suite or antivirus or something like that. And since users don't usually run netstat, that's possibly an interesting data point that could get flagged. So if I want to do this stuff without doing it the normal way, running the netstat command, and I have a whole programming language. So the netstat's forth file, which we can look at it briefly here. So here's forth code. And I don't want to go into the details too much here, but this is the code that does a netstat. And I've just loaded it in the system so I can run these words. They now exist in the dictionary. So I can see here all the running connections on this system, or I can see its routes. And this is all running within my process. I'm not creating another process which would increase my detection profile. I'm just using Win32 APIs. And this works out pretty well. It can be a really effective way to work through another system. So with that, I think this is a decent view of getting the system up and running, generating an agent, and then interacting with it some. I hope to do some more videos in the future where I may go into more detail about the language, especially because Forth isn't necessarily the most accessible language these days. It's just not very common. It's a perfectly wonderful language, in fact very expressive, but I think maybe I'll put some tutorial material together about how to use Forth just in general, and then also go through some more examples of developing some actual weaponized payloads, and hopefully make the system more accessible, and then make it clearer exactly what some of the values are for doing things this way. Actually, real quickly, because I geek out about this stuff so much, one thing I wanted to point out is we wrote that little function that just does something silly, but I wanted to point out that in the system you have full inspection of everything that you've done. So there's a function called see, which lets me see any of the words in the dictionary. And as useful as a hex dump is, there's one I added not too long ago that lets me see the full disassembly of the code. So actually test isn't quite so readable as parity is. So for example here, you can see each of the pieces of what that function does. So if you remember the code at all, this is the code that puts a 1 on the stack, and then this is the code that ands that with the number that was passed to the function, right? So we've got an and instruction here. And then even when we get to other things like the call instruction, if I take this address and check, I can see this is the call to the .odd function. So all of this is quite accessible, and you can see exactly what the compiler puts together anytime you write some code. So I wanted to include that too. I had forgotten to put it in the video originally. So anyway, thanks for watching.